Now we will see the problems based on the equations we have found. This is also important for the exam, so try to give attention. So what is the question? Problem 1. So we have a 25 kVA 7200 240 divided by 120 center tape single phase transformer operates at rated voltage. So it means we have the primary voltage 7200, secondary voltage we have 240 volt, and this is center taped. So this is based on the just taped out. So it means we are dividing the secondary voltage into 2 times. So that is what I think one of the student was talking about yesterday. So this is 120, 120. So now the totally we have 240 volt. So if you apply the basic circuit theory equation, this one is correct. This equation is correct. So 120 plus 120 is equal to 240. That is the secondary voltage. So now it supplies a single phase load that has an equivalent impedance of, you can see a load, an equivalent impedance of 7.2, and the angle is 36.9 degree. So load, it means ZL, we already know in the problem. ZL is equal to this value. Assume this is the ideal transformer and find these parameters. First, to find the turns ratio, that is nothing but A, and the secondary current, that is nothing but IS, and primary current, that is IP, and Z in seen from primary side. So you have to find the Z in value seen from primary side. Okay, so now we will find one by one. These are the 4 parameters we have to find, right? So for ideal transformers, the turns ratio A is equal to NP divided by NS is equal to EP divided by ES, or VP divided by VS, the same. So we know the primary voltage is 7200 volt and secondary voltage is 240 volt. Okay. So now we have to consider the secondary volt as a 240 volt. You cannot consider this as a 120 volt. Please remember the logic. I think, yeah, I know this is important for you to understand. It's a center taped transformer, but we are measuring the voltage between these 2 active lines. So it means we have to consider the voltage between these 2 lines as a 240 volt, not 120. That is the Vmax 240. Okay, so now 7200 divided by 240 is very easy to find the turns ratio. The first parameter is over. Secondary current. So how can we find the secondary current? So now you can see here, we know the Ohm's law. V is equal to IR. So Vs is equal to Is times Z. So Z is the impedance in the secondary side. So Is is equal to Vs divided by Z. You are bringing the Z to the left side. So now we know the Vs value, that is a 240 volt divided by this, what is this? This load impedance. So the load impedance value I have changed. The load impedance value is given here is 7.2. So now the new value is 6.9. So 6.9, and you can put the angle 0 degree minus 36.9. So that is going to be minus 36.9. When you divide the numerical, the angle should be subtracted. So minus 36.9. So now you have found already the secondary current. This is the second parameter. This is a very simple Ohm's law. Now you have to find the primary current. We already know how to write the turns ratio in terms of current. So IP divided by IS is equal to 1 divided by A. So we already know A value. What do we want? We want only this IP. So IP is equal to IS. You can bring it to this side. So IS divided by A. We already found IS value. That is 34.78. Angle is minus 36.9 degree. A value is 30. We found here. So we are just putting this and then finding this IP value. Please tell me if my value is not correct or if I calculated wrongly. And similarly, and the last one is called load impedance as seen from the primary side. So for this, you have to remember the formula. When we seen from the primary side, what is the formula? We have to divide by A square. Z load is equal to Z in divided by A square. Is it correct? From primary side, Z load is equal to Z in divided by A square, right? So that's correct. Z in divided by A square. So now we are, the question was, we have to find the Z in. So Z in is equal to Z load times A square. Z load we know already 6.9, the angle times 30 square. So you will get input impedance seen from primary side. So this is the fourth parameter. So that's all about this problem. They asked only 4 and we found all the 4 parameters, A, B, C, D. The second problem, we have 1 minute. I think we can finish it. The problem is like this, 300 kVA, that is the capacity. So 2400 to 120 volt transformer. Of course, the supply voltage has 60 hertz. This is the American system, or it's following the American standard. Single phase transformer operates at 2300 volts on the primary side. You see, operates at 2300 volts. You know, the here we have primary and secondary voltage, but this transformer is operating at 2300 volts on the primary side. So you should remember capacity. We always design the machine for certain capacity, but it works in the practical application. It works with the different loads and it gives a different power output. So the efficiency is always, we are calculating the efficiency in terms of output divided by input, right? That is a very standard formula for the efficiency. So for example, let's say this transformer, we can take this example now. So we have 120 volt, that is the VS secondary volt. And this transformer is designed for certain capacity. It's supposed to give that 120 volt at the secondary side of the transformer. We don't have a transformer here in the picture, but so we are applying 2400, but operating at 2300, and here we are getting 120 volt. Let us say we have the rectifier now. Rectifier means, let us just take it one simple half wave rectifier. So this is a diode, and we are connecting to this diode, and here we have the load. Maybe this is just load have only resistance property. It has no inductor. So R is the load, and we have the diode as the rectifier. So we are applying this 120 volt, and we are converting into the DC voltage. So now we can say the output delivered from the rectifier, output delivered by the rectifier divided by the input supplied by this transformer. We can also take it in the other way. We are designing some kind of power station with a certain capacity, whether we, for example, maybe we have like a 200 kilowatts power production we are expecting, but this power station is only producing 160 watts. 160 watts. So now how can you calculate the efficiency? 160, sorry, it's not a watts, this is kilowatts. 160 divided by 200. So if you calculate this, that is the efficiency of this power station. So this one is also depending upon the transformers used in this power station. So how efficiently you are utilizing the transformer. So you designed the capacity for 200 kilowatts, but it's only delivering us 160 kilowatts. So utilization factor is somewhere between 0 and 1. So this utilization factor we can use in all the machines actually, the efficiency calculations. So, but if we use this kind of utilization factor in transformer, then that is called a transformer utilization factor actually. Basic idea is output divided by input. This is the basic idea when we calculate the efficiency. So the transformer utilization factor, power factor, form factor, everything is kind of similar to each other, but they are not same. So we are calculating, for example, RMS divided by average value, or average divided by RMS value. You know RMS and average. RMS for the AC voltage and current. and average is for DC voltage and current. So it supplies 115 kVA to a load and has a power factor of 0.723 lagging. Assume ideal operation. So you have to find the secondary voltage. It means there is ES at operating voltage. Remember, operating voltage is 2300, and secondary current, that is IS, and impedance of the load as seen on the secondary side. Seen on the secondary side means that is from primary side. So now we have to find these parameters. So secondary voltage at operating voltage, that is ES at operating voltage. So we know turns ratio in terms of voltages. A is equal to VP divided by VS, or EP divided by ES, the same. So EP is the actual primary voltage is 2400 volt, right? 2400 volt, operating as 2300. So 2400 divided by 120, that is 20 volt. Ratio don't have a unit. So it's not a volt, it's not ampere, it's just 20. And A is equal to VP divided by VS, and VS is equal to, we are just bringing here, and then VP divided by A. VP, now we are considering the operating voltage, that is the 2300 volt instead of 2400. So 2300 divided by A, that is 20. But when we calculate the turns ratio, we have to use the original input and output, because the turns, based on the turns, this voltage will vary. But of course, the transformer can be operated at different values. So 2300 divided by 20, that is the VS. We have 115 volt. So that is what asked in the question, secondary voltage at operating voltage. Second question is secondary current, IS. So we know the P is equal to VI, V times I. So PS, power in the secondary side, is equal to VS times IS, voltage in the secondary time multiplied by current in the secondary winding. So now we want only IS. IS is equal to PS divided by VS. We are just bringing this VS to this down here. So now you can apply the values. PS what? That is the power in the secondary winding. It's already given in the problem. It supplies 115 kVA. So we are using that value, 115 times kilo kVA. So we are putting 10 to the power 3. So divided by PS, we just found 115. So we will get this 115 will be cancelled. So 10 to the power 3, that is 1000 ampere. So we found the second parameter also. We already found first, second. Now impedance of the load as seen from the secondary side. So load impedance is ZS is equal to VS divided by IS. That we know that the secondary side impedance is equal to secondary side voltage divided by secondary side current. So we already know VS, we already know IS. Then you can find directly this load impedance. ZS is equal to 0.115 ohm. And we also know power factor cos theta, they had given in the problem as a 0.723. Cos theta is equal to 0.723. Theta is equal to cos inverse 0.723. Just a calculator, you will find this value. So then finally you will find the complete load impedance together with its angle. So this is minus. So ZS is equal to 0.115. Angle is minus 43.7 degree. So what we had done here is we just used simple formulas. We derived some formulas. We derived this load impedance value seen from primary to secondary and from secondary to primary. And we are applying this, and also we know other basic equation, that is turns ratio in terms of voltage, turns ratio in terms of current. And yeah, that's all, I think, nothing else. And we are using those equations to make some calculations.